Hey, AP Stats, video number 2 on this activity involving power and later on errors. And so let's kind of refresh ourselves where we were. We're in a situation where our null is that the true proportion is 20%, which would be 13 out of 65 for these students opening cereal boxes, right? And so we've got this hypothesized null of 20%, and we think it might actually be, the true one might actually be lower. But we need to get a result that's pretty far away from it in order to reject a null. We said 7 boxes, which is 7 out of 65. I don't know, it's about 11% or something like that. We need to get 11% instead of 20%. We need to get 11% or lower before we're going to be convinced that it's like, whoa, okay, that 20% is wrong. So we said, well, what if it was only 15%? So what if it is lower, the null is false, but are we going to be able to detect that? Because we need to get a result that's even further, that's still a lot lower than that. And it turned out when we ran it that the first time I did it, me just doing 20 times, I only rejected the null 5% of the time. I only got 7 or less, which was the number we needed, 5% of the time. I did pretty lousy at noticing that the proportion was lower than they said it was. And then I ran the computer simulation, and then it was about 23% of the time. And we called this the power of the test. The power of the test is, for this situation, the power of this situation is the probability. The power is the probability of detecting the null as false when it actually is false. And my comment on it, I'm now going beyond it, was that, but it seems kind of hard to detect the null, like the false null. Like we're assuming it's 20% and it's actually 15%, but it's hard to notice that because a lot of results might be lower than my 20%, but not low enough to be very much convinced to go, well, that could just be sampling variability. And so a lot of weird things can happen, lower than 20%, but it's not weird enough for me to reject that assumption that I have, that 20% is correct. They actually did 1,000 trials, and they ended up getting about 23%. So yay, I was pretty good with my simulation. They did 1,000. I got the same number with only 400. Anyway, so it is not all that likely for students' test to detect a company if they go 15%. They could be cheating, but it's pretty hard to detect it. It says you have seen what power represents, and more general definition of power is below, but it's what I wrote above. It's the probability of detecting a false null when the null is actually false. Yeah? But now we want to talk about, and this is where you have to, so you should understand that definition of power, the probability of detecting the false null. And then you should, but now we're going to go into the next part, which is, well, what affects power? What affects the power of the test? On a test or something, like on a statistics test, you won't be required to calculate power. There's only been one time that people were required to calculate power, and it was on a question 6 where they were kind of walked through it. But you're not going to be required to. What's more important is that you know what it is, and then that you know what affects power. What affects your ability to detect when the null is false? Okay. So first question is, well, what if they change the sample size? So the students now, instead of doing the 65 boxes, before they did 65 boxes, and when the alpha was 0.05 and their alternative hypothesis was 0.15, so or the true proportion was 15%, then we found out the power is approximately 0.226 according to their stuff. So what would happen? Same situation, except what if they open more boxes? What would that do to affect power? That's the question we have. So suppose they did a second one, and now instead of doing 65, they're going to do 130. So in this situation with 130, you're going to conclude the company is cheating if you obtain 18 or fewer boxes with vouchers out of 130. And so now we're saying, okay, how are we going to do on this one? When are we going to detect the false null here? So let me get the calculator set up, and then we'll show you how this works. Okay, so I've got the calculator set up, ready to go. And so they worked out with an alpha of 0.05, that's how extreme things need to be for us to reject the null, that we need to get 18 or fewer boxes out of 130. So I'm doing that random binary thing. Whoop, there it is. Doing that random binary thing. Number of trials now is 130, and notice that it's now that the proportion is still 15%. And I'm wondering, so the null is false. It's 15%, not 20, but is it going to be a low enough result that I'm going to detect it? All right, here we go. Now it takes a little longer because now it has to do 130 runs of this thing, and it got 18. It got 18 boxes. So the first time, I'll tell you, 18 out of 130, they got 14%. So still kind of low, but 18, oh, that's good enough. That's extreme enough where you're going to reject the null. And so we're going to say a big yes to that. Whoop, whoop. Yes. We're going to reject the null here. We're going to reject the null that time. So we caught them. Ha! You company, you were low enough, and we detected that you were cheating on that time. All right, now we're going to do it again. So I'm doing random binary again. And this time I got 16. Even worse. They got 16 out of 130. So we caught them again. And that time we got 18 again. Whoop, caught them. We're on a roll. This time they got 24. So we wouldn't, if we found 24 boxes out of 130 with vouchers in them, we'd go, yeah, seems like no evidence against the null there, so we're totally fine. And so you can keep doing this and see how you do. Like, how many times do you detect a false null? So so far we're 3 out of 5. Next one, 16. Caught him! And so you can keep doing this. And if you want to, you can fill this thing out and run through all of them. I'm going to do it right now, and then I'll show you the results. Okay, I finished all 20 of them, just running those trials of, on the calculator, opening 130 boxes when 15% of them have vouchers in them on average. And so, but each time I might get different. Like every time I open a box, I've had a 15% chance of it having a DVD. And then seeing how many of them have the DVD vouchers. The voucher's not an actual DVD. Kind of weird. And so I'm finding out, well, okay, so how many do I get? And this shows how many boxes had vouchers each time. And there he did the calculation. You would reject the null if you got 18 or less, according to the workup above. And so now 1, 2, 3, 4, 5, 6, 7, 8. 8 times out of the 20, we caught them. We caught the fact that they were cheating. And so 8 out of 20, that's about 40%. That's exactly 40%. So according to our simulation, that's only 20, so we'd want to do it more. Remember, I was pretty far off when I did the earlier one because I got 5% when the real number is 23%, but that was just because, I'd only run it 20 times. But this is pretty clear evidence that, wow, if you increase the sample size, you're a lot more likely to catch it. And this should make intuitive sense. Think if a coin was off and it was like a 55% coin. If you only spin it 10 times, you're probably not going to notice. On average, you're going to get a 5 or a 6, and you're going to go, yeah, it looks like the coin's okay to me. But if you flip it longer and longer and longer and longer, and you keep going, you're going to notice it's going to be easier for you to see if the coin is off of 50%. So the larger the sample size, then the more power we have, the better the probability it is for us to catch it when the null is false. In the coin case, 50%. In the coupon case, the null is 20%. So 130, n equals 130 was definitely bigger. And so higher sample size and higher power. Yeah. You get how we're doing this? All right. So we're finding out what affects power. So now this is an interesting one. It's what if the value of HA changes? Or actually, I would like to say, what if the value of P changes, the true proportion? I like that a little better. What if the company is cheating with a value of P different from 0.15? Good question. Suppose they're cheating with a value of 0.10. So Earlier, we said, okay, they told us 20%, and now suppose they actually were cheating and they were only putting them in 15%. And then we figured out what the power, we approximated what the power of that situation is with alpha being 0.05. And we figured out the power was 0.223, 0.226, I think, the probability of catching him. So now what if instead they weren't cheating at 15%? What if they were cheating at 10%? That is, only 10% of the boxes have vouchers inside. How likely will it be for the student's 65 box test to catch them? Just take a moment. I want you to think about it and say, is that going to increase the power from 23%, or is it going to decrease the power? We're going to put the sample size back to 65. So back to 65. And so how does changing the true proportion affect our ability to catch it? All right, and what I'm going to do is I'm going to run my 20 trials. Remember that it's now 10% is the chance, but now also keep in mind that we're back to we need 7 or less to reject the null from just like we had earlier. All right, let's see what the results are, and I'll show you. Whoa, my God, we caught them a lot. Boy, that was a bad choice of them to be that far off. I caught it 15 times because I was at 7 or less, 15 out of the 20 times. Wait, 1, 2, 3, 4, 5. Yeah, only 5 times were the results not low enough for me to catch them. So it's definite that the which alternative p equals 0.1 gave us a lot more power. It gave us a lot higher probability of catching the fact that they cheated. And this should make intuitive sense on this, that the further off your null hypothesis is, that the easier it is to notice that the null is false. If I have a coin that's 51% heads, then I'm going to have a huge sample size for me to notice that it's off and that it's not a good coin. But if the coin is like 70% heads, I got a really good chance of noticing. And both the difference between those two is how far it's off from the hypothesized proportion of, I think it's 50% because it's a coin. That's the null. The null is that the proportion is 50%. The farther off you are from the null, the farther off the real number is from the null, the easier it is to catch them. So we've got a second way to have more power. Now, you don't have control over this. You can't, I can't make the coin different. But one example of a situation where somebody could have power is, what if I was going to set a card deck and I wanted to make a card deck that wasn't 50-50. I was going to make more black cards than red cards. Suppose I was going to do that. Then I could take out a ton of red cards and make it 90% black cards. And then, boy, people would notice it right away. The sample size could be pretty small, and people would notice it and go, that deck's not right. That thing, just keep picking black. But if it was what if I only switched it by 1 card? If it was a small difference between 50% and whatever I made the deck, then you'd have to do it forever to notice that there was a difference. So the farther off you are, the more power the test has, which means the greater likelihood you have of catching them. This one we're not gonna do this part. This looks at depending on what the true number is, it shows what the chance is, what the power is, what the chance is of you detecting it. And the farther you are from 20%, the greater your chance of catching them. This is called a power curve, and it's something you study later on in college, because that's what you're doing is you're making a curve of showing what would be our chances and how is that affected by how is our chance of catching them affected by what the true number could be. You don't have to do any of this, and it's okay. But specifically, as the distance increases, the power of the test increases. And now we're going to talk about significance level. I'll tell you one quick thing. Sometimes that difference is called the effect size. So the difference between the null and the true proportion, that difference, that's called the effect size. Bigger effect size, more power. Okay, we got one more and then some stuff about errors.